the lecture. This is lecture 5. So last time we proved the so-called no duality gap, and then we left this another big theorem, dual attainment, and along the way we introduced this so-called C-Legendre transform or C concavity and C convex functions basically. And then using these tools, we will today prove dual attainment. And then there's another big result in duality. I mean, the so-called complementary slackness. Okay, so complementary slackness is extremely important in optimal transport, and we will see what this result applies to optimal transport, in particular, to give us the so-called Brenius theorem. Okay, the Brenius theorem is like a bridge between optimal transport and partial differential equations. Okay, so optimal transport could be just regarded as just some optimization problem, but then after Brenius theorem, partial differential equations can be considered in that context. All right. So let's remember the duality. So here the primary problem is to minimize the total transport cost for transport planes having these given marginals mu and nu. So you want to basically transport this mass distribution mu to another mass distribution nu, okay, with certain transport planes, and then you want to minimize the transport cost. And the dual problem is like this. For each constraint in the primary problem, you have the corresponding dual variable. In this case, these dual variables are functions by themselves. They are, I mean, you can consider them as just continuous functions on those spaces. And then we have this constraint, okay, for dual variables. And this constraint is related to this cost function, this objective function in the primary problem. This C is the same C here, okay? So that's how duality works. And we proved the no duality gap and dual attainment last time in the context of optimal transport, assuming that X and Y are compact metric space and C is a continuous function. And C is the cost function, okay? And sorry, we proved no duality gap, and we will prove dual attainment and complementary slackness today. All right, and remember what the C-Legendre transform was. This is just the simple generalization of Legendre transform. Okay, so Legendre transform here instead have just x dot y, but we can put this general function negative cxy for general C. Then you can define this C-Legendre transform, and here, C convex functions are nothing but those functions coming from as a result of C Legendre transform, okay, of another function. And then yeah, I kind of discussed this. So these C convex functions, they share, and C Legendre transform, they share almost the same properties as Legendre transform, namely, remember in the Legendre transform, if you do Legendre transform triple times, that's the same as doing Legendre transform only one time. So this corresponds to this result here. You take C Legendre transform 3 times. That is the same as taking C Legendre transform only once. Okay, and here is another theorem that being a C convex function, it's the same as this double Legendre transform is equal to 5. Okay, so these are your exercises, and you really want to do these exercises, okay, to follow the course well. All right, and then why do you care about this? Okay, first of all, C convex functions, I mean, they are just a simple generalization of convex functions. So they share nice properties as convex functions. I mean, some features of convex functions. And complex functions are not arbitrary functions. They should be nice. So what kind of nice property do we want to consider? Okay, so there are some nice analytic properties of C complex functions. Let me just read this lemma. So if your cost function C is uniformly continuous, meaning the modulus it has for given, let's say, for given epsilon, it has same delta. It's like this. I mean, continuity is like that. So if you consider some space, let's say Z, continuity of a function is like at a point Z. If this is the value of your function, okay, then continuity means, if you like, given epsilon window, okay, you can find your delta window in your domain so that your function, whatever it looks like, okay, is inside, I mean, the graph of your function, I'm talking about the graph of your function is inside this like a product window in this in the product space. So that is spatial continuity. So you can, if you can find such window at every such point on the graph, then that is continuity. And equicontinuity means, uniform continuity means for each epsilon and at each z, the choice of such delta can be different. But then uniform continuity means this choice of this delta depends only on epsilon, not on each particular point z. That's uniform continuity. That is what is written here. Okay. And the good thing about the C convex function is this. If your C as a function of this product space is uniformly continuous, okay? In particular, if you consider, let's say, only this C Legendre transform, so this phi C is a function of Y, then if your C is as a function of X is uniformly continuous in X, then the corresponding Legendre transform is uniformly continuous, and it shares the same modulus of continuity. What is modulus of continuity is just a given epsilon. What can be your delta? That is modulus of continuity. So you can view delta as a function of epsilon. Then this function is called modulus of continuity. Of course, there is no unique such modulus of continuity. But some function, if you have some function like this, then you can have the same function for your result of C convex C Legendre transform. Okay. So this is something you can do, but let me not spend time on this because I'm going to do something similar in the next slide. Okay. And why do you care about such uniform continuity? If we had uniform continuity, then if you have family of functions having uniform continuity, meaning sharing the same modulus of continuity for all different functions, and then once you have additional condition that that family is uniformly bounded by the same whatever numbers, then such a family uniformly bounded and being uniform continuous for the same modulus of continuity, you have this so-called Arjala-Ascoli theorem, implying that such a family has convergence subsequence. So this is like an important consequence of having a uniform continuity of the family of each function and the family of those functions having the same modulus of continuity. Okay, so let me just be brief about this slide, and let me just move to the next one. So among uniform continuity, a very particular case is so-called Lipschitz continuity. So Lipschitzness is like this. Let me just copy the same, the previous picture here. So Lipschitzness is like this. Let me zoom in. Okay. So uniform continuity is that for each epsilon, at each z and epsilon, you need to be able to find some data so that this window contains the graph of your function passing through that point. Okay. Meaning the graph does not go outside. Okay. What is Lipschitzness? Lipschitzness is similar, but you don't have epsilon data anymore. Lipschitzness is like this. A function is Lipschitz, maybe more precisely, globally Lipschitz, if you can do the following thing at each point. Okay, so at each point Z, you have you consider the graph of the function. Okay, let me draw the graph again. This doesn't look Lipschitz. Okay, in such a way that the graph is contained in some kind of cone shape like this. Okay, so you can imagine some cone shape, like which is in this r direction. It has some kind of angle, right? But here you have just you can take any direction in z, but in r direction you can only go like this way. That's kind of cone. Okay, with some angle, bounded at some angle, bounded, so that your graph pass through this point and inside such point. Okay, so that is Lipschitzness. So if you can find such a cone at every point with the same angle, okay, then the function is Lipschitz. With some Lipschitz constant, this k in this expression is called the Lipschitz constant. Okay, and Lipschitz constant is just basically it's almost the same as the angle. Right? It's just relative quantity. Okay, if the angle is large, the Lipschitz constant is large. Angle is small, the Lipschitz constant is small. Okay, so that is Lipschitzness. Okay. And the theorem says, if your cost function is Lipschitz, then the result of this C-Legendre transform is also Lipschitz with the same Lipschitz constant. Okay. That is a theorem. And can you see why it should be the case? So to help you, let me remind you what the Legendre transform was. I mean, C convex functions are just given by some Legendre transform. Okay, so what should be like Legendre transform? Like it. So it is like soup over all, let's say in this case, x of minus c xy minus phi x. So this is a Legendre transform, and it takes supremum of the family of these functions. Okay. Now, by the way, I remember. Okay, I remember that I said something wrong in the previous slide, but we can fix it now. Okay, here, so we want to see Lipschitzness of this as a function of y, okay? And now, here on the right-hand side, we have this family of functions with a parameter x, but each member in the family is a function of y, okay? So here, y is only in this place, okay? So what does it look like? So each one now as a function of y, you have some function. Let me draw it this way, so something like this, like negative c x, and as a function of y. Okay, and this function depends on each x. For different x, you have different functions like that. Okay, and then what you know is that this function is, let's say we assume that this function is ellipsis. So at each point on the graph, you have some cone having some fixed angle containing the graph. All right, fine. Maybe I should draw this more in such a way that it can contain everything. Okay, all right. You see? Okay, now the C-Legendre transform is supremum of such functions. So imagine you have family of such functions, like something else, something else, something else, something else. Okay. But each one, at each point, it has the same cone containing the graph of that function. The same here. Okay. Imagine then this point is the same as that supremum value. Okay. Here. Because you may have other functions like this, and at that given y, you take a supremum of all these functions, and let's say we are here. The highest point is this one, so that's where we take supremum. Okay, then there, you can imagine that because each here is a supremum, so it has some nearby such a function like this, which is called supporting or C supporting function. They often call it this way. Okay. Such a C supporting function nearby, but that C supporting function has to be inside such a cone. Okay. Right? And if you find, then in a nearby point, you will have another cone like so another supporting function like this, and then your function will be we take the graph somewhere here. But the point is, such a graph of your C-Legendre transform also has this supporting hyperplane, supporting C supporting function, like from below, okay, and then there is something touching the graph, and of course it takes supremum, right, and then that one will also be inside the cone like this. So if you connect these pictures, you will see that all these points in the graph should be inside this cone. Okay? That's like a ellipsisness. So this probably is not perfect illustration, but this is basically the idea, and then you can prove this theorem, and the rest is exercise. Okay. I mean, you can do it more analytically, right? Just try to give some geometric intuition. Yes. This is, yeah, we are assuming that, yeah, the same. Yeah, it's a stronger condition. So you actually need only ellipsis in X with ellipsis constant K, also ellipsis in Y, ellipsis constant K. Yeah, probably not exactly the same. You will change the Lipschitz constant, or if you want to consider the whole Lipschitz in the product space. Okay, but they are basically equivalent. Okay, good. So then as a result, you can with Lipschitz cost function. What is the most important Lipschitz cost function? For example, Cxy is just the distance between x and y. This is Lipschitz function with Lipschitz constant. What is the Lipschitz constant? 1. Okay. Then your C convex functions with this cost function will have Lipschitz constant 1. Or it can be smaller, but not bigger. Okay. Then Lipschitz functions are uniformly continuous, right? At each delta, at each epsilon, you can find this window here giving this delta. Okay, so it's obvious that this expression just tells us that Lipschitz functions are continuous. I mean, it's even uniformly continuous. Okay, so you can apply Arjela-Ascoli theorem for Lipschitz functions as long as you have boundedness. Right? Okay. One more thing about maybe any other question about this Lipschitzness of C complex functions when the cost function C is Lipschitz from the Zoom? Any question? Okay, then let me move on. Even there's further properties of C complex functions. Okay. So it's like this. The first condition was about uniform continuity. It's like zeroth order condition somehow. And this Lipschitzness is somehow it is related to like differentiation. Okay. So like if you this angle, for example, will give you the bound on the derivative of that function at that point. So it is related to differentiation. So this is like first order condition. Actually, you can consider second order condition too, right? Something related to second derivative. Okay. Okay, what is it? It's called semi-convexity. What is semi-convexity? So a function in Rn is said to be semi-convex if you can make it a convex function by adding a parabola function like this. Okay. So how bad your semi-convexity is, it depends on how large such parabola function you want to put. You need to put. Okay. So for example, if the function is already convex, it is semi-convex because you don't have to add anything. Okay. And some functions like let's say example phi x equals negative x squared. So this is obviously not convex, right? This is but semi-convex. Why? Because you can just add x squared to it with k equal 1, then the resulting function is 0, which is a convex. Okay. So semi-convex functions are some kind of extension of convex functions, allowing you to add some parabola function like that. Okay. So analytically means if you differentiate, suppose you can differentiate the function, then the second derivative in this case is like -2, right? So, and convex functions have the second derivative of convex functions are non-negative, non-zero, non-negative. And semi-convex functions may have negative second derivatives, but their second derivative should not go to infinity. As long as the second derivative is bounded, then you can just add this large parabola function to cancel out the negative second derivative to make the resulting sum having non-negative second derivative. Okay, so that's how you may view semi-convex functions. So analytically, semi-convex functions are those having lower bounded second derivative. Okay, it doesn't need to have an upper bound, right? Because another example is, I mean, a function which is already convex like this is semi-convex, right? And it doesn't have upper bound of the second derivative because near zero, this function has infinite second derivative. Okay, am I making sense here? All right. So yeah,
I have a
just lower bound.
quick question.
Yes. Question?
So for a convex function, when you
Yes.
write that the Hessian should be greater than or equal to 0,
Yes, I mean,
can you remind me,
if you can find the Hessian, right? So actually, yes. What?
is it just the eigenvalues of the Hessian that need to be positive, or is that,
So
yeah.
yeah, right. So when we say the Hessian is over, or even for symmetric matrix, A, uh, A is non-negative is the same as all eigenvalues. So this notation does not mean each entry is non-negative. Okay. So this being non-negative is the same as this form. This quadratic form is non-negative. Okay.
Thank
Did
you.
I answer your question?
Yes, thank you.
Okay. And look at this function. This is nice function. Its graph looks like this. So you have this is minus x, right? And this function is nice, but it's not convex. Okay. And if you differentiate this, I mean, the second derivative here, of course, it's not differentiable, but you can imagine that this is like the limit of some function like this, okay? This is kind of limit, right? And then this function, if you make this kind of curve to have more and more sharp corner like this, then the second derivative will go to infinity, right? So this function, I mean, you can kind of define that some generalized second derivative, and in that generalized sense, the second derivative is infinity here, positive infinity. I'm sorry, negative infinity. Yeah, that's what I meant is negative infinity because it's a concave function. So negative infinity, so it doesn't have lower bound of second derivative. In other words, you cannot make it convex by adding any quadratic function like that. If you add quadratic functions, you will get something like, let me throw it this way. You will get something like so you cannot cancel this like corner shape. You can only get something like this. Okay. Here you will have this corner shape. You cannot cancel that singular shape near the origin. Okay. So here x plus any other function will look like, right? So you can do some similar games with other examples. Okay. So yeah, do this. This is your exercise. Okay. Okay. Then why do we say this about when we consider C complex functions? It's the same as before. If your cost function, let's say, is twice differentiable and uniformly bounded second derivative. So basically, it is a semi-convex function, okay? Because it has lower bound on the second derivative. Okay. So if you have such a function, basically the I should be careful about it. Yeah, at least let me just say this, just to be on the safe side. If your function is nice uniform second, having uniform second derivative, then the corresponding C convex function, all of them are also semi-convex, okay? And if with the same constant K here, I mean, this, the lower bound of this second derivative of the cos function, like, can be bigger than K. This K, by the way, can be, I mean, yeah, this lower bound can be negative. So it's like, if like negative K times identity. I mean, so this Hessian has this property, then your C convex function will be semi-convex, where you can just add K x Q over 2 to your function, then this one will be convex. Okay. This is your exercise, but let me just briefly say why it should be the case. So you can remember what this function, C Legendre transform, looking like. Okay, so C convex functions are given by some Legendre transform, right? So you just need to understand what the Legendre transform does. I mean, C Legendre transform does. So then you have this property here. Okay. So C has uniform lower bound. Okay. So that means, okay, that's why. So yin is uniform upper bound, right? Yeah. So negative C has uniform upper and lower bound. So at least it has upper bound for second derivative. So negative C has uniform lower bound, right? So this one is semi-convex, obviously. Each of these, okay. And then for each of these, you can just add this case the function y, this function, okay, on both sides. Okay. So here, this, you add this function on each side, but then this suprema is like, suprema is over x. So adding this is like adding a constant. So adding a constant to your family and take the supremum is the same as taking the supremum of your original family and add a constant after. Okay, so this is the same as adding this constant on the left. Okay, now this negative C has lower bound Hessian, but if you add this, and if the Hessian is low bounded by, let's say, I mean, the Hessian C is bounded by K, then if you just add this function, then that low bound of Hessian now, after this addition, will be 0, right? So then this, as a function of y, this is, you should view it as a function of y. This is a convex function after that, okay? Fine. But then you have to take the supremum of such a family of convex functions. And remember, supremum of family of convex functions is, again, convex. That's why you get convexity of this. So you get semi-convex. Okay, so the details is your exercise. Okay, so we just discussed these three nice properties. The basic message is that if you see the cos function has a nice analytic property, some kind of continuity or differentiability, ellipsisness, or like second differentiability, like semi-convexity, then the corresponding C Legendre transform or the C convex functions satisfy all the same properties with the same modulus of continuity or modulus of ellipsis constant or the semi-convexity constant. Am I making sense here? Okay, good.
So this
Any function having each function, if it has nice such property, then the C-Legendre transform also carries the same property. That's the message here. For ellipsisness, true. Also semi-convexity, true. Yeah, so any C convex functions satisfy such property coming from the cos function C. So for example, convex functions are, in our course is defined as a result of some Legendre transform. And there the cos function is what? Negative x dot y, right? Just a linear function. And linear functions are obviously semi-convex, right? And their second derivatives are zero. So the resulting C transform, which are just resulting Legendre transform, gives you semi-convex function. In this case, with k equals 0, so convex functions. Okay. And back for ellipsisness, if we consider the just the convex function case when cxy was just negative x dot y, so this as a function of either x or y, this is not necessarily ellipsis. Okay. As a function of x, this function has slope negative y, right? But negative y, I mean, if for example, if you are in Rn, negative y can be very large, right? So then this function may not be ellipsis. I mean, okay, for each given y is ellipsis, just a linear function. But then if you just write down the Legendre transform, then the Legendre transform has this family of such functions, okay? So if your x is in Rn, then this family as function of y has slope x, okay? And depending on your x, the slope can be very large. So you may not have uniformly bounded slope, okay? So this theorem does not necessarily apply because it assumes that the C has like the same, independent of x and y, it has ellipsis constant k. But here, if x is very large, you cannot bound it by ellipsis constant, any finite ellipsis constant k. Am I making sense here? But this one, you can, but if your x comes from some set, C is compact, C is some subset in Rn, compact, then the slopes of this x is bounded. So then you have this ellipsis constant applying to all such family. Then the resulting function is ellipsis. Okay. Get it? Okay, good. So that is relevant to this dual attainment theorem. Okay, now we can prove it. So what is dual attainment? So this is our dual formulation, and now we can even further assume that this phi and psi are continuous. Okay, satisfying this constraint. And we assume that x and y are compact metric spaces and C is continuous. Right. And the mu nu are probability measures here. Then the dual problem has an optimal solution, blah, blah. And importantly, the resulting optimal solution are C convex functions. Okay, so this phi bar is a C convex function. It's a result of C transform, and psi bar is a result of a C transform. And importantly, they are kind of paired in a close way that phi bar is the result of C transform of psi bar, and psi bar is the result of C transform of phi bar. Okay, right? So example of this related to the previous case is that x and y are closure or bounded open sets or in Rn, and cxy can be just a minus x dot y, or cxy, you can just consider this very important cos function, or cxy be like all these things apply, okay? Then you have such result. So how do you show such for dual attainment? Okay, as I mentioned in a previous lecture, the idea is the following. I mean, somehow we want to find an optimal solution of this nice objective function. The objective function is nice and continuous. It's a linear function. It's a continuous function. And then, but the feasible set here, those phi psi satisfying this constraint is very large, right? You just consider all continuous functions satisfying this condition. So it can be extremely large. So even if your function is very nice, continuous, but if the domain you want to optimize the function is very large, then you may not find an optimal solution, right? Sometimes, right? So, of course, your domain can be unbounded, and then your whatever, like maximizing sequence in this case, trying to maximize this function, can just move in that direction where the domain is unbounded, and just can go forever. So will not converge to anything. So the idea is to find some subset of this feasible set, okay, such that in that subset, two things, the subset is compact, okay, so that the corresponding objective function will have optimal solution, and the optimal value is still equal to this original optimal value. Okay, so that's the idea. Okay, get it? And we are going to use this C transform for that. Okay, why? The result of C transforms are nice functions. Okay, like ellipsis or uniformly continuous, and all these nice properties coming from the nice properties of the cos function C. So those functions resulting from C transform, the set of such functions will have certain compactness. Okay. Yes. So we want to reduce our dual functions into those C convex functions. So that's the idea. Okay, how does it go? Okay, so let's start with any, let's say, these dual functions, okay? Admissible. Admissibility means satisfying such a condition. I mean, the condition given in the constraint. Okay, then we know that because of this condition, what does this condition means? Phi x plus psi y is bigger than negative cxy for all xy. So that is this condition. So obviously phi y is bigger than negative cxy minus phi x for all xy, right? Then, so here, fix y and and then take supremum over X. Then still this one will be bigger than or equal to the supremum over X. But the supremum is exactly the 3 transform of phi. So that's why this side is bigger than this. So whenever you satisfy this, then one is bigger than the C transform of the other. And this is like obvious, right? Okay, then what? And then if you look at this objective function, you realize that because this one is bigger than this, okay, minus of it is less than minus of the other. So you can replace this negative of psi in this direction of inequality with this negative of phi, C transform of phi, right? Okay, so somehow you can reduce this pair phi psi into the pair phi C transform. Okay, then the corresponding objective function in this in the next pair is bigger than or equal to. So in the maximization problem, you don't have to consider this original one. You can just consider this one because it has already a bigger value than the other, right? Am I making sense? And then from here you can go further. Now you can play the same game to replace this with the systems of the other, right? Yeah. What? Here, I mean, I'm just using this, right? So you agree with, so his question, I'm just trying to understand his question, so let me not repeat his question. So, okay, so here, this one gives this inequality, right? And so you get negative size less than negative phi c. So then if you look at this, we have negative psi here, and this is a non-negative measure. So this part is less than or equal to this part. So then, yeah, original problem was about taking soup of all this. Yeah, so the soup of, okay, so let me answer his question and repeat his question at the same time. This question was, I think it was about, I mean, the original problem was taking the supremum of such expressions satisfying this. Then why then this one will give us right hand side can be infinite. Yeah. Yeah, just okay, so maybe just to be more maybe transparent, what I'm saying is this minus phi d mu minus psi d nu satisfying this phi psi c phi psi like continuous. I mean continuous is less than or equal to soup of the same thing with phi and phi C transform. So that is the thing. But look, another thing you want to see is here, phi plus phi C is always bigger than negative C, right? Okay. Am I making sense? This is always true. That is what called Young's inequality, which is obvious to see just from this expression. Okay. And then because of that, that is satisfying this condition, right? Am I making sense? So these pairs are subsets of all such feasible pairs. So then the corresponding supremum, because you have a smaller set, is smaller than the original one. But now you on one hand, that supremum should be bigger because of this inequality. On the other hand, because the set is administrable but still in a subset of this, so the supremum taking on a subset is smaller than or equal to the supremum of the over the original set. So that means this supremum is the same as that supremum. Okay. Now we can go further. We can do the same game with this expression. Now we have this. Now we can do the same game again. Then this phi is bigger than or equal to this. The Legendre transform of this phi c. Right? Yeah, we are just using the same expression again. The phi x is bigger than or equal to minus c xy minus phi cy, just coming from this, right? And then from there, you just take supremum over y. Then this is exactly the supremum of y will give the Legendre transform of phi c, which is phi c theta. Okay, fine, fine. Okay, then this expression can also be further bounded by this expression. Okay, so you get, and you can do the same thing again. Then this expression, which is this, can also be bounded by this expression. And along the way, all such pairs given here are admissible. They satisfy the constraint that their direct sum is bigger than or equal to negative c. Okay, so that means because of the same principle as before, the supremum taken over these more special pairs is the same as the supremum of the original problem. Am I making sense here? James, am I making sense here? Did I start recording? I think I did, because the icon is this one, red, so it's okay, right? So the implication is the original supremum. Let me just copy it here. The original supremum is the same as the supremum of the same function but with different with a smaller, much smaller subset of admissible pairs. Namely, these subsets are just coming from these pairs. Okay, but remember, if you do the triple C transform, you get this. I mean, so these are nothing but, all these are nothing but C convex functions, right? This is C convex function, C convex function. So you can just consider them as phi is C convex function of the other, psi is C convex function of the other. Am I making sense? Fine. Okay. So this supremum is the same as this, and this is in the subset. Okay. So to maximize this functional in this original set can be reduced to finding a maximum of the function in this smaller set. Am I making sense here? Okay, then we just need to examine this reduced problem. Okay, and then C convex functions, remember, if your C is uniform continuous, but in our case, our C is continuous, but the space is a complex space. So that means your C is uniformly continuous. I mean, continuous function on a complex space is uniform continuous. So C is uniform continuous with some modulus of continuity. And then if you do the C transforms, then those results are uniformly continuous. Again, with the same modulus of continuity. So all C convex functions, they came from the same cost function C with a modulus of continuity. We share all of those C convex functions. We share the same modulus of continuity. Am I making sense? They all have the same modulus of continuity. In fancy words, it means they are all equicontinuous. Just another name for having the same modulus of continuity. Okay? Right? Questions so far? So family of all C convex functions in this context is equicontinuous with the modulus of continuity the same as the modulus of continuity of the cost function C. Am I making sense here? Okay, fine, good, good. Okay, okay. Now, then we are very close to using to being able to use Agile-Ascoli. But for Agile-Ascoli, if you remember the statement, I mean, equicontinuity of the family is not necessary because, for example, you may have sequence of functions. Just let's say you can just add constant to the sequence of functions. Then the values of the functions will go to infinity, so no convergence. So in Agile-Ascoli theorem, you need some boundedness of the function, uniform boundedness of the function. Namely, the family of functions all need to be bounded by the same constant. Okay, that is what you also need to have Agile-Ascoli compactness. Okay, so that's the context of the next exercise. So basically it says, in fact, you can adjust the problem, this problem a little bit so that you can assume that all these relevant functions are uniformly bounded. Okay. Okay. Do you understand my question? Do you understand the exercise? Okay. And do you understand how to do it? And do you know how to do it?
You want to use the fact that the spaces are X and Y are compact, and then fix a base point and use the fact that you can add and subtract a constant.
Okay. Very good. So everybody heard it, right? So the idea is that, I mean, it's like this. You have some kind of functions having the same modulus of continuity, but these functions, let's say this is R, this is your space, let's say, I don't know, X or Y, right? Then these functions can go to like infinity. So you may not have any like convergence sequence. But the thing is, his idea is, okay, for these, I mean, the functions having like large value, let's say you just fix one point in your domain that you just bring all these down by some adding constant. So you can just make everything, let's say, at x0 be 0. So you will have some functions like this and other functions like that, all passing through this 0 point at x0. Okay, by adding constant by adding minus phi x0 for each phi. Okay, the constant depends on phi, right? But then, okay, and then you have all other functions psi. all other functions psi, and then you just make that just fix on y0, and then you make all these psi functions also pass through such reference point. Okay, so by adding negative psi y0. Okay. I have to be careful here. Sorry. Okay, this part is not exactly what I want. Okay, now for the y part, and what he mentioned is extremely important. You add, so here you have, let's say, phi and psi. Let's say they are paired. Let's say you have phi is phi c, sorry, psi c, and psi is phi c theta. So when they are paired, so when you modify this phi by this adding this constant, you want to modify psi with the same constant but opposite sign. Okay, why are we doing this? It's like this. If in the original expression here of the objective function here, you have these two integrals. So if you add some or subtract some constant there, so you will have this integral of that constant time of the constant times the integral of d mu, right? If you add constant, you will have this additional one term. But then you will change the objective function. So, but you don't want to change the objective function. So then you want to subtract the same constant, okay? But then how do you get, how do you subtract? But this subtraction can be added here because mu and nu have the same total mass. That's the reason why this calculation works. So adding constant to one function phi is the same as subtracting that constant to the other function psi, then the objective function still remains the same because mu and nu have the same total mass. Okay, so you do this. Okay, then at least for this family, you have this unit kind of phi, the family of phi, they all pass through x0, but they are all continuous, uniformly continuous, and x is compact. So all these now these reduced functions are bounded by the same They are just bounded by some same uniform constant. Okay, so you have boundedness here, but then all these psi functions after that will be C transform of all these functions here. So if the functions are bounded and C are bounded, C is bounded, then the corresponding C Legendre transform taking supremum or infinite is still bounded. So that's why you get boundedness for all these pairs, phi and psi given by this. Okay, by just adding one constant there and then subtracting that same constant from the other. Okay, so then you can apply Ajala-Ascoli. Then you have convergence subsequence, which converges. And then the function, the object function is continuous in this with respect to such an operation. So such a sequence. So the objective function will converge to the supremum, which is the maximum value. Okay, and then your resulting whatever this limit will be an optimal solution. Okay, and that being optimal solution means that the resulting one should still be admissible. They are continuous because just Ajala-Ascoli theorem, the limit of such family is continuous. But then maybe the only question is whether these such pairs in the limit satisfy the conditions we wanted. Okay, in particular, not just admissibility, but in the theorem we just want them to be like C transform of each other. Okay, and the last part is your exercise. Okay, question? Okay, so let me move on. Okay, once you have dual attainment, you have then primal solution and dual solution. I mean, you have primal optimal transfer plan. We already had. Now we have dual optimal solutions. Okay, and that primal optimal solution, I mean, optimal transfer plan, and then these dual optimal solutions, they have relations. Namely, the prime optimal solution is a measure on the product space. Some measure there has support only where this bar side bar satisfy this equation. I mean, we already had, remember, this is a general effect for this bar side bar because they satisfy the constraint. Okay, this is general effect. And then what this equation says, I mean, the set of xy satisfying equality is kind of special set. I mean, for this inequality, any point works, but for that equation, only very special set would work, right? So then this means your optimized transport plan should support it on some special set. Okay? Am I making sense here? Fine. I mean, it may look not so impressive, but you will see why this is an impressive result. Anyways, why this is true? It's very easy. I mean, the primal optimal value and dual optimal value are equal with this optimal transport plan and dual optimal solutions. I mean, that's what we proved, right? No duality gap. And then now you can rewrite this as this. Making sense? Why? Because this pi bar has marginal mu and nu. So if you integrate this, while this phi bar has only x variable, psi bar has only y variable, the integral of phi bar with respect to this pi bar xy will be reduced to integral of this pi bar marginalized at in x variable. The same for the y variable part. So that's why this is equal to this. So then this expression can be written in this way. Okay. Okay. So this is your exercise, but I already told. So then now here we know that this is always non-negative and this is always non-negative, and the result is 0. The integral of non-negative object is 0. That means all this inside one has to be 0. That means this product is 0. That means this guy will not be non-zero whenever this is non-zero. Okay, so it should be non-zero only when the left-hand side is 0. That's this result. Okay, good. So that's complementary slackness, and why is so important. And that complementary slackness, if you translate it in a proper way, that gives this extremely important theorem in optimal transport. Maybe this is the probably the second most important theorem in optimal transport. The first most important theorem is Kantorovich duality. And then maybe this is the second most important one, Brownian theorem. Second or third, I mean, at least to me, it's the second most important thing. Okay, what Brownian theorem tells is the following, that let's say you consider some bounded open sets and take closure. And then let's consider this quadratic cost function and probability measures on x and y. And let's assume that one of them is absolutely continuous with respect to the back. So this means mu is the mu as a measure is some function, some kind of some kind of, it has some kind of density function. Okay. Okay. Actually, it's L1. That's the meaning. And then the optimal transfer problem with this particular cost function. Okay, we already know that optimal solutions exist. There exists optimal transfer plans. But here the point is that such optimal solution is unique. This is very non-trivial. Not only that, and this is very important part, and this is why Brownian theorem is so powerful, is that the optimal transfer plan gives some kind of measure on the product space, right? But Brownian theorem says that measure is actually supported on the graph of certain function from x to y, okay? And optimal transfer plan is just supported there. And then you can further say that there is this map kind of pushes forward this measure mu to nu. So this map is like you have, let's say, let me draw it this way. You have mu and nu and your particles here and particles there. And you have kind of mapping from the domain of mu to domain of nu so that you kind of transport the mass following that mapping. Okay. This is not exactly the same as the transport plans. Transport plans, this is a mapping. And transport plans, in general, given mu and nu, what transport plans can do is, for each x, it doesn't have to provide only one target value y, but it can go to several locations from one x. That's what transport plan can do. But Brownian theorem says, in this context, the optimal transport plan is only given by this optimal mappings that x goes to only one y. Okay? Yeah, that is called Monge map. I already said it's a Monge solution. And not only that, and further, even further, okay, then mapping, okay, I mean, it's already remarkable that optimal transform is given by a mapping. I don't think you can easily do it by other way. It's not a very non-trivial result. And more interestingly, such a map has this very special nature. It is gradient of a convex function. The Brownian theorem is very remarkable in the sense that it connects optimal transport with just Euclidean convex analysis. Okay? And so now, after this, you will see later, then it has connection to the so-called Monge amplification, which I mentioned previously. It looks like this: determinant of Hessian of that function is given by the ratio of, in this case, mu x and nu gradient to something like this. So this is like highly non-trivial partial differential equation. You have Hessian but determinate. So they call it full, not just nonlinear, fully nonlinear PDE. So Brownian theorem connect this interesting optimal transfer problem to this very interesting partial differential equations, long-term equation. Maybe let me write it again. Nu of gradient ux. It's just view mu and nu having this density with the same notation, mu and nu. Okay. All right. So yeah, so here in this particular case, your source measure is absolutely that's what required. Right. So it's a very good point. So here, when I said these are equal, so for this transport plan, we are talking about moving mass, right? So whatever happening where there's no mass, it doesn't matter, right? So this mapping may still, as a mapping on this like a domain X, may still not be a mapping. It may like send a point to several locations, but such a thing happens only when that point doesn't carry any mass. Okay, so that's why I say it's a mapping. It's almost every sense. For almost, so it's I think I should be more careful. It should be mu almost every x. For mu almost every x, actually in this case almost every year. Okay, but to define such a measurable mapping is like it's a mapping mu almost every sense. But in fact, the mapping is given as the gradient of a convex function almost every sense. Okay, I mean, it's just because mu is absolutely continuous to this to the back. Okay, and then so here, the right-hand side requires differentiation of convex function, but the convex function corresponding to Brownian solution here may not necessarily be differentiable. Okay, so this differentiation is like almost every sense. So you can differentiate that corresponding solution almost every sense. Then that almost every derivative is equal to that almost every mapping T. That's what this theorem says. Okay. And I don't think I have any further more time to discuss why that complementary slackness gives this Brownian theorem. If you want, you can read the remaining pages, but maybe it doesn't necessarily explain it. So probably, okay, let me come back with this connection between the complementary slackness and the Brownian theorem later when I resume my lectures, okay? But at the moment, you just accept this as a known result, and you can just assume that it came from complementary slackness. Okay, that is something you can just remember from now, and then from Monday for I think for 2 weeks, Professor Paul will give lectures and at different time and obviously different location, only in Zoom. Okay, not in this room anymore, but I think he will give lectures at different time. I don't remember, probably evening time. So check the website or Slack, then the information will be there. Okay, so okay, I will come back after these 2 weeks of break for me. Okay, good. Okay, let me stop now.
Thank you, Professor. I have a question.
Hold on, let me stop sharing.